Hi, we are from Group 2. We are going to present you the improving production quality of power bank units using 7 QC tools. These are the 4 issues that you can see on the slide: the overheating during charging, the short battery life, the unresponsive power button, and the inaccurate battery level indicator. These tables already shown that the number of the complaints for each issues, and from here you can see that our major issue is the overheating during charging, which has 120 for the number of complaints, and together all issues the total number of complaints are 340. So here is our table of content, which we will further discuss later on. First is the flowchart of the power bank assembly and testing process. Next is the cause and effect diagram for our major issues, which is the overheating, the check sheet using sample complaint data, the histogram of the complaints, the parameter chart, the scatter diagram showing the relationship between the temperature and charging time, and the control chart for the battery capacity measurements.
Hi, I'm Darshi Nair Gobinathan. I'm here to present one of the QC tool, which is flowchart. This flowchart shows the manufacturing and quality inspection process for a battery pack assembly from start to finish. Above shown the flowchart, and I will be explained step by step of each stage of the process. From the start column, the beginning of the battery manufacturing process. Next, battery cell inspection. The battery cells are visually and technically inspected to ensure they are meet the required standard. Acceptable, which is the decision point. If the cells are acceptable, the process continues. If not acceptable, the product is rejected or discarded, leading directly to the end. Furthermore, battery protection circuit soldering. The safety circuit is soldering to the battery cell to prevent overcharging, short circuit, and etc. Additionally, PCB board assembly. Print circuit board is assembled which control the power distribution and other electronic function. Then, microcontroller programmer. The microcontroller is programmed with software to control the battery system operation. Moreover, power button and LED display installation. Power button and LED display are installed to allow user interaction and battery status monitoring. Continue with the battery cell insertion into the casting. The assembler battery is inserted into its outer casting for protection and durability. Initial charging test. A first charging test is done to make sure the battery charged correctly without overcharging or failure. Functionality test. The battery pack is tested to ensure all functions such as charging, discharging, LED button are work properly. Temperature monitoring during charging. While charging, the battery temperature is monitored to ensure safe operation. Battery life stimulation test. The stimulation test is run to check the battery long-term performance, like how well its remain capacity over cycle. Final virtual inspection. A final check is done is to ensure the product look and function as expected. Pass, which is another decision point. If the product pass, it goes to packaging. If it's failed, the process ends and the product will reject or send to rework. And last process is the packaging and labeling. Pass battery packed and are packed and labeled for distribution. And the end of the production and inspection process. This flowchart outlines a detailed quality-focused process for battery manufacturing, including inspection, programming, assembly, and multiple stages of testing to ensure the battery is safe, functional, and reliable before packaging. For this presentation, I construct the battery pack manufacturing process flowchart using Draw.io, which is an online diagramming tool also known as DiagramNet. It's allowed for flexible creation of flowchart, process map, and system diagram with wide variety of shape and connector. First, I list down all the steps involved in the battery manufacturing and testing process based on our topic. This helped me identify which steps were action and which were decision point. Since I want to show the sequence and decision logic clearly, I choose to create a flowchart. Flowchart is ideal for visualizing step-by-step process with clear direction and checks. I use ellipse for start and end point, rectangular for action step like battery inspection, diamond for decision point like acceptable or pass. I connect the shape using arrow to indicate the flow of the process. I make sure that each decision point had clear yes/no path to reflect real-life quality contract logic. To make the control chart visually organized, I use different colors to highlight start, end point, action, and decision step. This helps the viewer quickly identify the structure and critical part in the process. I arrange the layer in the clear horizontal sequence, adjust elements, and check the logical flow. After that, I export the diagram as an image for use in the presentation. Why I choose Diagram.io? It is free and easy to use. It supports outline and offline access. It's offered drop and drag simplicity for rapid design. It's allowed saving and exposing in multiple formats including PNG, JPEG, and PDF. This tool helped me visually present the entire battery manufacturing and inspection workflow in a professional and structural format. That's all from me. Thank you.
Okay, Assalamualaikum and salam sejahtera to Dr. Sharia. My name is Muhammad Mirzan Ali bin Ansar Ali, matrix number SA23075. Okay, my part is I would like to present about the analyzing of the overheat issue in power banks using a fishbone diagram, also known as a cause and effect diagram. We identified overheating during charging as a main problem and broke it down to 6 categories: human error, low quality material, manufacturing error, processing method, measurement error, and also poor environment. Under the human error, we found that technicians may not properly train and inspection are often skipped. For low quality material, the use of substandard batteries and poor insulation contributes to overheating. In manufacturing error, faulty equipment like damaged soldering tools or broken temperature sensor can cause charging problem. Okay, and then under processing method, we noticed that important steps such as temperature testing are sometimes missing or not followed properly. Measurement error includes the use of inaccurate temperature tool and the absence of clear overheating limit. Lastly, poor environment means high room temperature, poor ventilation and humidity, all of which can affect the battery performance. Today, and then to address these causes, we have proposed several practical solutions. For human error, proper training, and the use of detailed inspection checklists are necessary. To solve the low quality material issue, we suggest using only high-grade batteries and reliable insulation. Manufacturing error can be reduced by maintaining machines regularly and replacing any faulty part. Then improving the processing method involves adding proper cooling tests and enforcing complete testing procedure. To fix measurement error, we recommend choosing tools and clearly setting safe temperature limit. And poor environment, installing better ventilation and maintaining a controlled room temperature will help prevent overheating. By addressing these root causes with the right solution, we believe the overheating problem can be reduced and the overall product quality can be greatly improved. So that's all from me. Thank you, Doctor.
Assalamualaikum, my name is Sharifah Rizalina Rauha binti Said Ismail, SA22016. So I will present my part, which is a check sheet and histogram that is using sample complaints that is generated by ChatGPT. The check sheet is used to collect and categorize each complaint systematically. It helps us keep track on how often each type of problems was reported based on the customer complaints. For this analysis, we recorded 4 main types of complaints, which is overheating during charging, short battery life, unresponsive power button, and inaccurate battery level indicator. The data was tailed and totaled using a sample table format. So from the result, we found that the most frequent issue was overheating with 120 complaints, and followed by inaccurate battery level indicator with 55 complaints, and short battery life with 80 complaints, and finally the unresponsive power button with 45 complaints. So this tool helps us clearly identify the most urgent problem here. The next QC tool is histogram. So I use histogram to visualize the data from the check sheet. This tool presents the frequency each of the issues in the bar chart format, making it easier to understand the distribution problems. So on the x-axis, we have the 4 major issues, while on the y-axis, we have the number of complaints. So as you can see, the bar for overheating issues is the tallest, followed by the inaccurate battery level indicator issues, while the unresponsive power button is the lowest. So the histogram makes it visually clear which problems are the most serious and need immediate attention. So, based from the analysis from both check sheet and histogram, we can summarize the findings such as overheating during charging is the biggest issue reported, which may indicate problems in thermal management design. The second one is inaccurate battery level indicators could point to issues in software calibration or sensor quality. Short battery life such as possible inconsistencies in battery cell quality or capacity. And the last one is unresponsive power buttons may caused by poor contact points or weak material selection. So based on these findings, our proposed solution would be redesigning the thermal insulation and using higher grade of circuits to manage that during charging. Based on the findings that I have presented earlier, our proposed solutions including redesigning the thermal insulation and using higher grade circuits to manage heat during charging. The second solution is by improving software algorithms for battery level readings and testing calibration accuracy. The next solution is by sourcing higher quality battery cells or increasing quality control during incoming inspection. And the last solution is reinforcing the mechanical design of the power button and conducting durability tests.
Assalamualaikum and a very good day to Doctor. My name is Nur Afika binti Muhammad Nur with ID matric SA22017. So for my part, we can see from the Pareto chart, we can see that top two contributors complaints are first one, overheating during charging, which is 120 complaints, and second, inaccurate battery level indicator, which is 95 complaints. So these two issues account for more than 80% of total complaints, making them the critical areas for improvement. So let's move on to the issues. First issue, overheating during charging. So the root cause is low quality charging components. So low quality charging components such as the charging integrated circuit, resistor, capacitor, power transistor, and connectors, or so on. Lack of proper material standards such as low-grade metals or plastic that conduct heat poorly or degrade quickly. As the result, during charging, these components will heat up quickly under load. So, to improve these causes, so we need to use high quality components with heat resistance. So one of the solution is find the company sourcing, which is choose the components from reliable suppliers with ISO certified manufacturing process. Or another solution is implement the thermal profiling test during R&D and quality control to ensure all the charging components remain within safe temperature range. So for the next issue is inaccurate battery level indicator, which is the heat cause is inaccurate voltage or current sensing circuits. So this means battery level indicators rely on internal circuits that measure voltage, current, and sometimes temperature to estimate the state of charge, SOC, of the battery. However, if the sensing circuits are poorly calibrated or the low precision sensors, then the system may give a false battery level reading, such as showing 20% of battery remaining when it suddenly dropped to 5%. And for the improvements or solutions, we need to regular firmware update to correct the battery readings. So for example, enhance the battery management source, which is firmware updates should include improved algorithm for estimating SOC using techniques like such as Coulomb counting, that is tracking in or out current. So that's all for my part. Thank you.
Hi, I'm Yazin. I will be presenting the analysis using the scatter diagram showing the relationship between the temperature and charging time. As you can see in the plot, each data point represents one full charging cycle. The x-axis showing the charging time in minutes and the y-axis shows the temperature in degrees Celsius. From the data, I found a strong positive correlation between charging time and temperature, which is the calculated Pearson correlation coefficient is equals to 0.83, indicates a strong linear relationship. More specifically, I observed that once charging exceeds 90 minutes, surface temperaure often exceeds 45 degrees Celsius, which is the maximum safe touch limit recommended by the safety standards such as UL. This trend suggests that prolonged constant current charging and the poor thermal management are the key contributors to overheating. Based on this, I propose the following actions. First, we can apply a firmware update to reduce the constant current phase by approximately 15%. By shortening the constant current window, we immediately cut the heat generated during the later part of the charge cycle. The solution for the poor heat dissipation is to replace the current thermal pad with 1 mm graphite heat spreader. The thicker graphite layer lowers the thermal resistance, allowing the heat to escape the cell stack far more efficiently. Other than that, add the surface-mounted NTC thermistor to trigger real-time tapering for the root cause of no dynamic temperature control. This sensor gives us the live feedback. The charger will automatically reduce the current if the surface temperature rises too quickly. Moreover, for the user overcharged overnight, we can update the user manual and app with smart charge reminders. Clear guidance and push notification will educate the users and prevent unnecessary heat-inducing overnight charging sessions. So for this scatter diagram work, I use ChatGPT as the AI tool. First, I use an AI-powered data cleaning script to screen the 40 raw charge cycle records, automatically flagging and removing any invalid temperature readings caused by the loose thermocouple contacts. Second, the Pearson correlation coefficient that I mentioned just now was calculated in seconds using the AI Analytics notebook. We also generated the annotated plot that you see on the screen. Third, I applied the predictive AI model that stimulates charge temperature curves under new firmware parameters. This helps us to confirm that tapering the constant current phase by 15% will indeed keep case temperature below 45 degrees Celsius. So by automating data validation, statistical analysis, and what if the stimulation with AI, I shortened the cycle from raw data to actionable insight from days to just a few hours. In short, by using the scatter diagram, it helps us to establish that long charging duration correlates strongly with the surface overheating, mainly due to the firmware behavior and thermal design. Now moving on the last QC tool, which is the control chart, which we use to monitor the consistency of the battery capacity across the production lots. I analyzed 25 subgroups, each consisting of 5 units, and plotted their average battery capacities. The statistical control limits were calculated based on the process variation. The center line, also known as the process average, is 10,017.98 mAh. The upper control limit UCL is 10,186.45 mAh, and the lower control limit LCL is 9,849.5 mAh. Any subgroup outside these limits is considered to be influenced by special cause variation. In our control chart, I detected 5 out of control subgroups. Subgroups 1, 8, and 17 exceeded the UCL indicated the overfilling, while subgroups 5 and 20 fell below the LCL indicating underfilling. Upon investigation, the main causes were traced to drift in, pneumatic fuel head pressure drift, and manual override of recalibration steps after clogging. To correct this, I propose with some solutions. First, we can replace with barometric fuel heads, closed loop control for pneumatic fuel head drift, because swapping pressure-based fuel heads for barometric units will eliminate the pressure drift and guarantees consistent electrolyte volume. We also can enforce the lockout procedure so that recalibration is mandatory after any manual maintenance. And we also can set up the real-time SPC alarms to trigger when subgroups average approach ±2 sigma, helping us intervene immediately. And for the operator inconsistency, we can retrain the operators on the calibration protocols and SPC response, which means focus retraining standardizes the best practices across all shifts, closing the human factor gap. These changes aim to improve the process capability to a CPK, which is the process capability index of at least 1.33 and reduce capacity-related complaints by over 60%. In this work, I also use the ChatGPT for generate out the control chart. First, I ingest 125 individual capacity readings, calculate the subgroup averages, and instantly set the center line and the control limits as you already heard that I mentioned just now. And it continuously monitors fuel head pressure data and predicts drift up to 30 minutes before it would push a subgroup beyond ±2 sigma. Finally, it assembly to become this control chart graphic. And in conclusion, this control chart It helped us to reveal the special cost variation in battery capacity driven by the inconsistency in the fuel head system. Last but not least, for the AI tools declaration statement, we use the Draw OI to generate out the flowchart. We also use the ChatGPT to generate sample complaint data for the check sheet and histogram, fishbone diagram, parallel chart, scatter diagram, and the control chart were drafted using the stimulated data with assistance from ChatGPT 2. All outputs was interpreted by the team and adjusted to fit the project scenario. And that's all for us. Thank you.